Hello, everybody. I'm Dr. Shafiq, and I would like to welcome all of you in this video session. Today, in this video, actually, we'll be talking about the design considerations for slope stability analysis. Okay, design considerations. So let's move forward and see. So you can see for the evaluation of the slope stability that requires establishing a design condition or loading condition to which the slope may be subjected during its life. Okay, so I'm going to talk about the design conditions or loading conditions in the next page. And then I must have to also include the performance analysis of stability cases. So if you talk about the stability cases, then basically you can see that during and at the end of construction, usually we call that one short-term stability, okay? Then we have long-term stability, which means like steady state seepage, like will establish by that time, okay? I'm just talking about when your slope has water at both sides, okay? Or your embankment or dam has water at both sides. Once again, like if you don't have any water there, then basically the life would be very, very simple and your analysis would be very simple. But if you have water in like different water level at different side of the slope, then basically seepage will occurring and there will be pore water pressure, different pore water pressure at different locations. As a result, your effective stress, normal effective stress at the failure plane would be different. And we know if the normal stress is different, then basically your shear strength would be also different, okay? So as we see that pore water pressure changes from one point to another point, that also changes the shear strength of the soil and the stability of the slope would be different at different conditions. Okay, so the second one is long-term stability. Third one is sudden drawdown. Sometimes we also call that one rapid drawdown, which means like if you have very high water level on one side of the slope, but it drops down very quickly, so that the soil cannot drain by the time when you drop the, like your stage, means like your elevation of water. And if you change that one fast enough that the pore water pressure, which was there because of the long-term stability or long-term, like flow, seepage flow, steady state seepage flow, that would be hampered and the water cannot get out from there very quickly. That's the sudden drawdown. We'll definitely talk about that in the next part. And then earthquake loading. What happens like earthquake when happens? Uh, Now you know that the earthquake potential is not same like every place. Some place has very high potential. Let's say like western part of US, let's say the California, Oregon, or Washington state, they have very high potential for earthquake. On the other hand, if you think about the east part of United States, they don't have that much, potential for earthquake. So in the eastern part, if you want to construct a, um, let's say a large dam, then basically earthquake will not be a governing factor there. But once you try to do that one in the western part of United States, let's say somewhere in California, then basically earthquake loading will be very, very significant. Now, the first three cases are static and the fourth involves dynamic loading. Okay, so in this, the first three actually is from your manual from the U.S. Army Corps of Engineers that I provided you. So you can just go there and also take a look from there, because this presentation is based on that design consideration, which is presented on that manual. Okay. The fourth one involves the dynamic loading. Actually, we'll not talking about the whole analysis, but we'll just try to see that what are the terms and how we can avoid any impact on our slope because of the earthquake loading. Okay. Now let's talk about that design condition, that what are the loading conditions that we have to consider for each of these cases. Okay, for each of these cases. So these are the following parameters that you must have to consider based on the stability cases. Okay. Now, what are those? Like the shear strength, pore water pressure, unit weight of soil, external loading that's working on the slope, and tensile stresses and vertical cracks, or the cracks that develop because of the tensile stress, or sometimes we call that one tensile cracks. Okay, so is there any tensile cracks or not? Now, the most important thing would be like what shear strength parameter you are going to use for stability analysis. Okay, so this one will change like what cases you are talking about. If you talk about like short term, then we are going to use one type of shear strength. When we are talking about long term, basically in the long run, everything will be drained out. So basically we are going to use drain shear strength in most of the cases. Um, and and let's say like for sudden drawdown, you will see at the beginning, we can just talk about like that drain strength. And when this one, the stage falls suddenly, then basically we have to use undrained shear strength. So we'll talk each of that factors, like separately for each of the cases. Okay. Now, usually these are the selecting, like these are the factors that must have to be considered about shear strength, that whether you are going to use drain strength or undrained shear strength, laboratory strength test, like what kind of test you are trying to do in the laboratory, type of strength envelope, whether this one is linear or non-linear, stress strain behavior means like how you are going to pick the strength. Is it based on like peak stress, or is it like a strain based or something like that? And then peak fully softened and residual shear strain, that what you are going to do. As I said in our other video, that usually for long-term performance, we try to use the fully softened if this is like a clay material. Okay. And for short term, maybe like the peak strength would be fine. And then we have to talk about strength anisotropy, like whether they show any directional change of the strength, and then strain compatibility, like how fast we are applying the strain in the laboratory, and how does this one compare with the field condition. And the creep effect means like whether the load is there for a prolonged period, then how the soil will behave. So based on all these factors, I have to just choose what shear strength parameters of the soil I'm going to use for the stability analysis. Okay. Now the second one is our pore water pressure. Okay. For effective stress analysis, pore water pressure must be known, because your effective stress is nothing but the total stress minus pore water pressure. So we can calculate like what is the total stress based on the weight of the soil and other loading here. And then we subtract the pore water pressure at the bottom of that slice, let's say here. Then basically we can find out the effective stress. Once we know the effective stress, then we can find out the strength of soil in terms of effective stress, right? So for total stress analysis, we'll talk about that actually, what is like total stress analysis and what is effective stress analysis. The pore water pressure are specified as 0, although in fact the pore water pressure are not 0. Okay. So for long-term effect, even though the pore water pressure is there, but if we talk about like the total stress analysis, which is actually we do when the sudden drawdown occurs, so that's actually UU, undrained condition. So we usually use UU, so phi equal to 0 situation. So in that situation, actually, we don't use the pore water pressure as in the field, we just assume that one is 0. Okay. So pore water pressure can be determined from these 4 different ways, like field measurement, hydrostatic water pressure, flow nets, finite element seepage analysis. Actually, this one is very common, like for existing, like dams or something. This one is the easiest one. You just try to assume that there is no flow is occurring. Flow nets was very popular in the past because it's very fast for a steady state seepage condition, and finite element seepage analysis is most accurate, and we usually do that one whenever we have the software. It's very easy, very accurate. So let's see like what are all those methods to find out the pore water pressure. So pore water pressure measured from the field. So only applicable to existing slope where steady state seepage has developed. So if you see any big dam, you will see that there are a lot of piezometer installed at the other side, back side of the slope, okay, at different depth and different location, so that you know that what is the pore water pressure, especially like if you want to find out, like for long-term stability analysis, then basically the steady state seepage condition will, develop there, and then basically you can read that one directly from the field. At the time of measurement, pressures may not represent the most critical design condition. This is very, very true. Like, let's say um, the water level is not that high, like you measure that one. But when this one is like flat time or something, then this water level will go down. So the seepage would be much higher at that time, because your seepage is a function of the head difference, right? But usually for bigger dams, actually I was working in Corps of Engineers, and there was like 4 dams under my supervision. So we used to take data every week, okay? And they have been taking that data for 30, 40 years, okay? And try to see that what is the maximum possible, like flow there, okay? This one is subjected to various measurement and interpretation of the errors. And sometimes we might need like interpolation of the data if you want to change the location from one uh, place to another place. Usually values of pressure are available at only a few points. Some interpolation and some extrapolation requires for other points, okay? And we also see like the practical consideration. I saw that many of the piezometer, like what they installed many, many years back, is not functioning well, okay? So if you run the um, numerical model, actually you can see some of them are not working that good, okay? Because of the age of the instrument. Anyway, so that's one of the way to measure the pore water pressure for the existing slope. Then pore water pressure computation directly from the hydrostatic computation. It's the easiest way, okay? So if you know the height of the water here, then basically at the bottom of that slice, you can say what is the height. If this is the height, then the pore water pressure would be gamma W ZW, okay? So gamma W, unit weight of water, and this is the height. That's the way you can do that one. But not many situations actually would be that simple, because the other side of the slope might have a different water level. When the water level is different, then basically the flow will occur. When the flow occurs, then basically your uh, you cannot use that simplistic, like the formula to find out the constant total head. The third one, pore water pressure from the flow nets. Okay, if you know that the water height in one side is here, the other side is, let's say, here at the bottom, but the water is seeping like here. This is the seeping line here. Okay, then basically you have to use the flow nets to find out the pore water pressure. So what you usually do, we just um, try to find out the uh, head loss because of that whole thing here. So what we usually do, determine the total head at the entrance and the exit of the flow region. Let's say this is 40 and this is 12 here. Okay, so the difference of head is basically 28. Now determine the change in head per equipotential drop, that how many equipotential drop I have from here to here. So you can see, actually, this is the actual head here. This is 1 drop, 2 drop, 3 drop, 4 drop, 5 drop, 6, 7, 8, 9 drops. Okay, so equipotential drop is 28 by 9, which is 3.11 meter. But you have to be very careful, like when you are counting that one from here, then this is not a drop. This section is not a drop. The first drop is here. Okay, you are just going down using a staircase. So the first step down here is this one. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8. Actually 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So for each of that, here you are just dropping 3.19 meter. Now you just determine the number of equipotential drop. We already did that one, and compute the total head loss. So for Z, for that point Z here, you can see my drop is actually, these are equipotential lines. So here is equal the same potential, means like head here and also here. Okay, so here you can see like 1 and 2. So total loss is 2 into 3.11. So that's 6.22. So the head at Z here, that's 40 minus 6.22. Okay, you can also go like from here, like 12 plus 1, 2, 3, 4, 5, 6, 7. 7 into 3.11. So you have to add here, you have to subtract if you want to go from that side. Okay, so the head at Z is 33.78 meter. So the pore water pressure at Z has to be 9.81, which is the gamma W, and this is your height. So this one has to be 331.4 kPa. That's the way, you can just find out your pore water pressure at any node. And if you see like, hey, this one and this one, but you want to find out something in the middle or within that 2 points somewhere else, then basically you have to interpolate or extrapolate sometimes, like to find out the uh, estimated pore water pressure when the steady state seepage condition occurs. And then you can do that one for numerical computation. You can just use either finite element or finite difference software. Actually, we are going to use GeoSlope, which has GeoSeep, that we can run and try to find out what is the pore water pressure in each of the nodes here. This is kind of like finite difference grid, but the software we are going to use, that's a finite element softwares, and you will just get like different type of grids and nodes, which may be more like advantageous than this one here. So this is your upstream, this is your downstream. If you show the water level here and here, then basically this one will show you how the distribution of the pore water pressure at different nodes based on steady state solution. Okay. And this one is saying like if you use like finite difference analysis, and if you know the pore water pressure and pore water pressure, then basically you have to adjust, like if you want to find out that one, then basically you can just try to get the average of that two. Okay. So kind of like interpolation. Now unit weight of soil is the kind of like the driving force that's gonna take the soil down, okay? Because the slope would occur a component of the weight of the soil along the slope down there, okay? So the total unit weight for both total stress analysis and effective stress analysis are recommended, okay? So we never use submerged into water, whether this one is underwater or not. So we all the time consider the total weight, okay, total weight of the soil or unit weight of the soil, okay? If this is saturated or like it's below the water table, then the system pore water pressure automatically, will be calculated. So we don't want to, like confuse that one. For unit weight, we always try to consider the total unit weight, okay, not the submerged one. Now, external loading. What are the external loading working on that? So all external loads imposed on the slope or ground surface should be included in the slope stability analysis, okay? So you can see here what are the different type of, this is the water pressure that's coming from here, okay? So water pressure is equal in every direction. So you have to find out like, hey, how much this one is going like perpendicular to that surface here, okay? And you can see the water pressure is here. And if you have any surcharge on the slope, then basically you have to show that one here. If this is a road embankment, then basically there will be a lot of traffic loading that you have to show there. And sometimes you can see there is like a tension crack that develops in the high plasticity soil when the climate is very dry or weather is very dry, all the water will go away. And if the water content is lower than the shrinkage limit, then basically you will see that soil will try to shrink a little bit and a lot of tension crack will develop, okay? So these are the loads like you must have to consider, like water pressure, any structural load. Like if you have like any roadway here, then you have to show that one here. And then surcharge load. This is your surcharge load. Let's say your traffic load, then anchor force and hawser force. These are the like sometimes if you see that there is any anchor here or hawser here, like that's kind of like there is a boat here and you're just trying to anchor that one with that slope, then basically you must have to show that one there, okay? And slope stability analysis must satisfy the force equilibrium regardless of the total or effective stress are used to specify the shear strength. So it doesn't matter what kind of shear strength values you are gonna use, but the overall equilibrium means like summation of fx and summation of fy and summation of a moment has to be 0, okay? That's the basic, like understanding of the stability analysis, that your equations for static must have to be satisfied. So tensile crack, soil usually doesn't have any like tension. Sometimes they might have a little bit, but we usually neglect that one. Significant tensile strength can be found for unsaturated soil, especially like the clay soil. When they dry, you will see they have very strong, like looks like a rock. But the problem is like when this one will be saturated, you will see that the clay will just, all the tensile force will, go away. So that's why we usually don't consider any tensile strength of the soil for any analysis. And you can see here that basically these are the cracks that form at the top of the, usually very common at the top of the slope here. So likely become filled. Sometimes that can be filled with water. Okay. So I have to show the water pressure on this part. Okay, because we are gonna take this part off from our calculation because the failure will not occur along that line because there is already a crack here. So this one is gonna fail along that line here. Okay, so we are not gonna consider that one here, but we have to show the force, water force. If it is filled with water, then like the water pressure like in this direction perpendicular to that surface. Okay, and this depth of the vertical crack often be estimated from the Rankin's earth pressure theory. Okay, if you just try to see that you have clay soil, and if you follow the Rankin's earth pressure, then basically you can find out the depth of the tension crack. So that's the way you have to consider the tensile crack, because you can see if they don't have any crack, then basically you have to add this shear strength for failure. When you already have that crack, then basically the shear strength here doesn't, doesn't play any role for that failure here. Okay, so if you have tension crack, that means like this slope can fail easier than if you don't have any cracks. Okay. Now, stability analysis, we are talking about the stability cases now. Okay, this is like the short-term stability or like stability during and after the construction. So for short-term, what we do for shear strength, we use drain strength for free draining materials, okay? And undrained shear strength for materials that drained slowly. So it's kind of like a compromise, like that how fast your, like construction is going on. If you think like, hey, the construction is going to take like 2 years and your soil can drain in like in a year and a half, then basically you can use drainage strength. Okay, if you see like, no, the soil is going to drain only 50% that time, then you cannot use that drain strength anymore because that would be a little bit risky. Okay, so in that situation, you can use definitely undrained shear strength. If you see, no, it's only like 5% consolidation occur, or the pore water pressure, excess pore water pressure cannot dissipate or like consolidated within the time frame of the construction, then basically you have to use the undrained shear strength. Okay. Now, sometimes stage construction may be necessary for embankments built on soft clay foundation. So basically, you are trying to allow the soil in the foundation to consolidate it, and the excess pore water pressure will be dissipated before you start the next stage. Okay, so that's called the stage construction. Means like the first year you are doing, let's say, 4 feet. Next year you are coming there and you are doing another 4 or 6 feet and then another 4 or 6 feet. So in 3 years, you just constructed 20 feet or 30 feet stage by stage. So every time, let's say you were working 3 months to construct that one, then you were taking 9 months off so that the soil in the foundation, the clay soil in the foundation, get chance to dissipate all the excess pore water pressure by that time. And in that situation, you can use consolidated undrained triaxial test. If you see that during that stage, like the difference between that stage, like 1 year and then like 3 months construction period and then 9 months, and then you are going to start the next stage. So if you see the consolidation is partial, then basically you can use strength from the CU test. Okay. Now, pore water pressure. How do you measure the pore water pressure for short-term stability? So basically that depends on, again, like what type of soil you were talking about. If you think that during that construction period, the steady state seepage, like flow has achieved, then basically you use the pore water pressure from the seepage analysis. If you see, no, the still, like the water didn't go to the other part of the, um, slope and still going very slowly, in that situation, you can just use the hydrostatic pressure. Now, I got that one from the manual, Corps of Engineers manual. So this one is basically saying the same thing here, that during construction or end of the construction, so what shear strength parameter and pore water pressure values you are going to take. So this one is like for free draining soils, use drain shear strength related to the effective stress, and for low permeability soil, use undrained shear strength to total stress. If it is completely undrained, so we use UU condition phi equal to 0. So in that situation, this is the total stress analysis. Okay. And then pore water pressure, it's saying the same thing what we talked about. Like the pore water pressure can be estimated using analytical techniques such as hydrostatic pressure computation if there is no flow, no steady flow yet, and the seepage, like method, or like use the flow nets or finite element method to find out the seepage pressure there. Okay. And same thing here too. Now, external loading. One of the important load that's coming from the water. Okay. So what is the critical pull level for the construction stability? So for short term, usually we use the minimum pull level for the upstream slope stability. Why we do that one? Because the water also creates some pressure on the soil, so it doesn't fail. Okay, it doesn't fail in the short term. Okay, so if your water level is low, then this force is going down, so you have the maximum chance when this pull level is minimum for short term. But once you see that um, the the seepage, like steady state seepage has developed, then basically this condition may not be necessary. Okay, a higher pull level for the stability of the downstream slope. But if you want to do the slope at the downstream, then basically you have to show the highest point of the pull. Okay, because this one is trying to force this way, so the other side of the slope can fail from that, like pressure. Now, long-term stability. Okay, so when we do the long-term stability, means like when after the construction, sufficient time has passed so that the steady state seepage is occurring now. Okay, so usually these are very, very common for earth dams. Okay, not for, let's say, highway embankment, even though there's some part has like water, but the water can dry very easily, and steady state seepage is not that common there. So this steady state seepage thing is more common in dams, okay, where one side has a lot of water, other side doesn't have. Now, shear strength, what kind of shear strength we use for long-term stability? We use drain shear strength because in the long term, all the, like pore water pressure will be dissipated, okay? Because even like very um, low permeability soil, like uh, in the long run, sometimes it has to be dissipated completely, right? Our consolidated soil will be consolidated completely. And that's actually your long term, okay? So that's why for long term, we always use the drain shear strength. Pore water pressure, like the where would be the pool for both upstream and downstream slope stability analysis. The critical pole level for steady state flow is the maximum water level or surcharge storage level or maximum water level. Usually the spillway crest elevation, okay? The maximum that it can hold at upstream, okay? The maximum is the hold. Sometimes there should be a spillway when the stability of the dam is under question. They open that spillway so that some of the water can drain out from that spillway. So this is say the maximum storage is basically the top of the spillway. Okay. The tailwater level should be appropriate based on field condition. So that depends on like how low you want to keep the other side. Let's say for levees, you want to make sure the other side there shouldn't be any water, right? So actually, what's the difference between dam and levee? Dam is across the river, okay? And one side you have higher pool, the other side you have very lower pool. What is levee? Levee is actually along the river, not across the river. So that during the flood time, the water cannot go to the bank of the river or the catchment area, okay? So in the levee may not be working when in dry season, okay? It's just sitting there. But dam is not like that. The dam always they have like the uh, level of water is different, okay? It's changing, even though in dry condition, this one is going a little down, and in rainy season, this one is gonna go a little up, but actually never this one will be same, okay? So that's basically the biggest difference, and that it has very important impact on the performance of the slope. So this is also again from your from the manual, and you can see the steady state seepage condition. You always use the drain shear strength. Doesn't matter like what kind of soil is that, and then you can just measure the pore water pressure, like based on hydrostatic pressure when no flow condition or steady state analysis technique using flow nets and finite, not numerical methods, like to find out the pore water pressure at different location. What about the external loading? The surface pool is usually higher than the storage pool that adds a load for the driving force of the water, okay, for both upstream and downstream slope cases. The tailwater level should be appropriate based on the field condition, like how low you want to keep that one. But here, what happens like when you open that spillway and you have like more water here, the water will just go very fast through the spillway, okay? That creates a velocity head. It's v squared by g, right? So that's why usually the external loading at storage level would be little higher than the storage level, okay? Now, long-term instability analysis, how do you do that one? Well, first we use the drain strength expressed in terms of effective stress parameters. Okay, compute the total force on the slice. Equilibrium requires a balance of the total force. What is that slice and everything? We don't know yet, okay, because we didn't talk about that. We are going to talk about like a couple of weeks later, okay? So basically this one is not like, you will not completely understand that one. Maybe I'll talk about that when I go there. Now, stability for sudden or rapid drawdown. Okay, so you can see the before drawdown, this one was here. Okay, and not suddenly, let's say in 7 days, this one is coming from here to here because you open the, maybe there is another, like a dam in the other side, and you open that, like gate over there. So the water is gonna go very rapidly from here to here, let's say for 7 days. And you can see when the water was here before the drawdown, then basically there was a steady state seepage condition. So water was flowing from this side to that side, okay? So these soils are basically completely saturated. But you can see when you drop that water from here to here in 7 days, but the water to seep out from there to this level takes, let's say, for 3 months. So in that situation, a undrained, like situation occurs because the soil here is now undrained condition, okay? The soil here, because here is your after drawdown water. So all the water that was there when before the drawdown has to, drain from here because your water table has moved from here to here. And let's say that takes 6 months, but you change that water level, let's say in 7 or 14 days. So basically an undrained situation will occur here. Now, if you change that water level very slowly, let's say for 6 months and going slowly from here to here, you will see the water will also drain very slowly. So this is not a problem at all, okay? But when you change that stage very quickly, that the water in the soil, the saturated part of the soil cannot drain out during that period of drawdown, then basically you have a different case here. Okay, that's we call the sudden or rapid drawdown case. The sudden drawdown analysis involves 3 stages of analysis. 3 stage. You have to do 3 different stage. Okay, we'll talk about that when we do that one. Okay, but for now, you just try to see what we do is like in the first stage, the effective stress along the surface, shear surface to which the soil is consolidated prior to drawdown is calculated. So what we do here, like let's say there is water here, okay? Now this water is creating pressure here, right? So actually this is, let's say this is your failure plane. So the soil here will be compressed from that load when the water is here. So we need to see that because this one was there for a long period of time, so this force will cause, you can see there's a lot of force here compared to here. So here will be consolidation much more higher than the consolidation that occurs here because the load is here is much lower. Okay, so the first stage actually we try to see that, hey, what is the consolidation or how much consolidation has occurred there, okay? The second stage competition is the undrained shear strength of the consolidated soil that are estimated from the reservoir when this is lower. So basically, the second stage is like change that water from here to here and find out the undrained shear strength here based on the consolidation that occurred during the first stage. Okay. And then we do the third stage computation. That's basically do after the drawdown, analyzing using the lower of the drained and undrained strength obtained from the computation from the prior stage. What does it mean? That means like your usually undrained shear strength is lower than your drained shear strength. Okay, so the drained shear strength goes like this, like slope, and your undrained shear strength is horizontal. But you see that when your sigma is very, very low, in that situation, actually, your undrained shear strength is even higher than your drained shear strength. Okay, so for very low, uh, effective stress. I'll show that one when I do that one very clearly. So we want to make sure that we are using the lowest shear strength to make sure that failure doesn't occur because of the sudden drawdown. Okay. So here they already talked about like what I told you, that sudden drawdown for free drainage soil, use undrained drain shear strength related to the effective stress. And they are talking about all the 3 stages here and how you consider the pore water pressure. Just read that one. I already talked about that in the earlier slides. Now we are talking about earthquake loading. These are kind of like some information you need to know to understand what's going on there. Okay. So first of all, like earthquake loading is usually a short-term duration because the earthquake doesn't happen like for 3 hours, 4 hours. It's just like maybe 20 seconds, like a minute or so. It involves motion in the horizontal and both vertical direction. Okay. It can cause any of the following problem to any slope: settlement, cracking of the embankment near the crest of the dam, instability of the up and downstream slope of the dam, differential movement between the embankment, abutment, and spillway structure leading to cracks, liquefaction or loose in sand shear strength, overtopping of the dam by wave due to earthquake-induced landslide, differential movement of fault passing through the dam foundation, etc. Okay, there are a lot of things can happen, but we cannot like prevent anything based on like what you are expecting there. Okay, but some of the things you can prevent. Okay, and definitely we'll be talking about that when we just go there in details. Okay. Now, earthquake mechanism and the ground motion. So earthquake results when the stress within the earth build up over a long period of time until they exceed the strength of the rock. So you know that we have like certain number of tectonic plate, like in the bedrock, right? So if you see there are a lot of stress, like generating, like in the soil that exceed the strength of the rock, then there could be a fracture. And when it fracture occurs, then basically earthquake happens. Now you can see here like different type of cases we are talking about. This is like, this one is going down, this one is going up. So this is basically a normal fault, we call that one, okay? Reverse fault, when this one is actually going, this is because of the compression, this is because of the tension here, okay? This is tension, that's why this one is moving away from this one. Here, actually, this is like compression. So you are just pushing that one and this one is going over that one, okay? And The third one is strike, slip, fault. This one is actually like moving like this, not like this. This one is moving like this way. Okay, so this type, three different type of reasons that can cause, like the earthquake. And the earthquake occur along the fault means like the uh, weakest point of the link. Okay, the weakest point of the tectonic plate that will break down where this massive, stress develop. Now, these are some of the terms that you need to remember here, that where this one occur, like here, actually this uh, fault is slipping away. So that's the location inside the earth. This is the earth surface here. So we call that one focus or hypocenter. If you just go directly above the point on the surface, we call that one epicenter. Okay. And this is the point of interest. Let's say I have a seismic, like instrument here. Okay, so I just measured that one here. I just want to see how far this one from the epicentral distance, like from here to here. Okay, and the distance from here to here is hypocentral distance. Actually, this is not that much important, but this epicentral distance is very, very important. Okay, because this is the location of the epicenter, and then I'm trying to see that, hey, how much problem occurred at different location from the epicenter. And I have like several, like seismometer, like installed here, maybe here, and the other side on that direction, like let's say this is 100 kilometers, this is 75 kilometers, the other one is 200 kilometers. So I can understand the actual, the intensity and magnitude of my earthquake. Okay, so these distance are very, very important. And now focal depth. This is the depth from epicenter to the focus. That's actually your focal depth. And we talked about epicentral distance, that from here to here. Now you can see these are two different type of seismometer that you can measure the magnitude of the earthquake. So this is basically the vertical earth motion. You can measure with this one, and this is the horizontal earth motion. There are a lot of things inside there. I don't want to go there, but actually you can see here that if this one moves, then basically this one creates some, like line on that. This is a pane here. This is the rotating drum. So for, let's say if it happens for 2 minutes, then the paper will rotate and this one will create like, like the vibration along this, like way. And this is your horizontal, like movement. So here is the pen. If it moves like that, then basically the pen will move like this and create that, like a diagram here. From there, you can just, like find out that how much movement has occurred. Okay. Now, what type of wave that we see from the earthquake? So there is body wave and there is surface wave. So body waves, these waves travel in the dimension through the earth. There are two types, P and S wave. Okay, so P is the primary wave. So these are compressional wave that particle motion, parallel to the direction of the propagation. Okay, so here you can see, if you see that one, like here is compression, here is tension, and then here is compression, tension. So it's kind of like going like this, okay, going like this. And then secondary wave, these are shear wave, which is perpendicular to the direction of the wave. Okay, so that's your shear wave. Okay, so this one has like right angle to the direction of the propagation. If this one is propagate like that, this one is going like this. here this one is going like this. Okay, so amplitude of S wave is greater than the P waves. Okay, here the amplitude is much bigger than this one. This is the wavelength, right? So here the wavelength is shorter, here is the wavelength is faster. So P wave travels through rock faster than S wave, thus they arrive at seismograph before the S wave. So this wave is faster than this wave. So you see first the P wave and then you see the S wave, okay? And what is surface waves? These waves travel over the two-dimensional surface like ripple on a pond, and there are two types rely on the lava waves. So you can see this one is going like this at the surface, okay? And this one is going like this. The difference is this is in surface and this is like within the earth material, okay? Now, magnitude of the earthquake. This is kind of important because that's the magnitude is the physical size of the earthquake. Magnitude can be determined from the data recorded by the seismometer, okay? So first of all, let's say what is Richter scale or local or Richter magnitude, okay? So that's a very, like common for the layman term, like people want to see that one, but basically this one is not used that much for the scientific calculation or anything anymore, but they have like some, like relation all the time. You can see here that basically this is the based on maximum seismic wave amplitude recorded from the standard seismograph at a distance of 100 kilometers from the epicenter, okay? If you have like, you don't have like 100-meter away, you don't have any seismometer installed there, okay? Let's say it's 90 kilometers or 150 kilometers. Then basically you have to make some correction from there. That's the factor you do that one. This is log A. A is the maximum amplitude that you record, okay? So that's the way you try to find out this one from here. But most correctly for scientific people, usually we use the moment magnitude. What is that moment magnitude? It is based on physical properties of the earthquake derived from an analysis of all waveforms recorded from the shaking. This one is only from the maximum, but this one is not. So what is that one? This one is 2/3 of log moment minus 10.7. Now, what is that moment here? That moment is basically rigidity multiplied by the area multiplied the slip. What is the rigidity? Rigidity is the strength of the rock along the fault. Area is the area of the fault that slipped. And slip is the distance the fault moved. So how much area, how much is moved, and what type of rock we are talking about. Okay, so based on that we can just get like your N naught. So you can see if like let's say the rigidity doesn't change that much from rock to rock because they are all tectonic plates, maybe not that much variation is expected here, but the area and the slip, this is more important. If this one happens in a small area, then basically the magnitude would be very low. But if you are talking about a massive area and the slip is very high, then basically your magnitude would be of the earthquake would be very, very high, okay? But you can remember these are all log scale here, okay? Even the Richter scale, this is like rock scale. Now you can see the stronger rock material or a larger area or more movement in an earthquake will contribute to produce large magnitude of the earthquake. Now you can see here that The magnitude scale is not linear. These are just, like log scale. Each step represents 30-fold increase in the energy released by the earthquake. Okay, so basically the magnitude 5 earthquake represents 900 times than magnitude 3. Okay, so each of that thing is like 30 times. So from 3 to 4 is 30 times, from 4 to 5 is 30 times, so total is 900 times. So magnitude 4 earthquake ruptures a fault area about 1 square kilometer, and magnitude 5 about 10 square kilometer, and magnitude 6 about 100 square kilometer. Okay, and then this is basically, you can just try to find out like the relationship between different type of magnitudes. Like this is your ML, a local or a Richter scale magnitude, and this is your moment magnitudes. Okay, so for each of that case, you have different, like line here. From there, actually, if you know the moment magnitude, then you just go there and try to see that which, parameters you are looking for, and then you can find out that one from here. Okay, so you can see if your moment magnitude is 4, then basically your Richter scale, that's also 4. And this one remains, this is your ML. Okay, this one remains almost like up to this point, 6 level, 6 scale, moment magnitude is actually like 6 magnitude, like Richter scale too. But then this one is going a little down here. Okay, so here you can see if this is like 7 magnitude, like your moment magnitude is 7, then basically your Richter scale would be around 6 point, let's say 7. Okay, so that's the little difference there. Now, what is earthquake intensity? Magnitude actually talk about like how big areas, like will be affected. And earthquake intensity is the measure of shaking at each location, because as far as it goes from the epicenter, you can understand the effect would be lower and lower, right? Depending mostly on the distance from the fault rupture area. Now, the intensity also depends on the direction of the earthquake rupture and what type of surface geology we are talking about, okay? So if you have like rock, then basically this one propagates very easily. If they have like soft soil, then basically this one will be dumped very fast, okay? So it depends on what kind of, like soil is there. The intensity scale consists of a series of certain key responses such as people awakening, movement of the furniture, damage to the chimneys, and finally total destruction. Okay, so intensity that depends on where you are with respect to the focus, like where this one happened, or with respect to your epicenter. Okay, if you are close to the epicenter, for same magnitude, your intensity would be highest. If you are going away from the epicenter, so your intensity will go down, 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 and at a certain distance, you will not feel that one at all. Okay, the intensity scale that we use in the United States is called the modified Mercalli intensity scale, but we usually don't hear that one that much. We most of the time hear about that what Richter scale, like is uh, the magnitude of the earthquake. Now, characteristics of earthquake. Sites underlain by stiff soil and thick cohesionless soil may experience similar peak acceleration to the bedrock values. Okay, The ground acceleration for the site underlain by soft or medium clay may be different from the bedrock accelerations, usually lower than that. However, the Mexico earthquake in 1985, where the bedrock acceleration was 0.03 g, g um, is the acceleration due to gravity, and the peak acceleration was 0.17 were recorded at the surface of the soft soil areas. Okay, so it's not true that all the time this one will be lower than that. So even for soft soil, we see that the peak acceleration go high. Okay, at very high acceleration, let's say greater than 0.3 g, the peak acceleration may be attenuated because of energy dissipation, whereas ground acceleration less than 0.1 can be amplified. Okay, so if it is already 0.3 g, then the chance of damping is very much expected. On the other hand, if the ground acceleration is less than 0.1 g, then there is a chance that this one will amplify. Now, what happens like for earthen structure, most importantly, actually liquefaction is that can happen to any earthen structure. So the cyclic loading causes densification of soil. When the soil is saturated, the tendency to decrease volume is counteracted by the increase in pore water pressure and decrease in effective stress. So you are just trying to, let's say, shake something. So this one will try to densify. But if the soil is saturated, then when this one will try to densify, actually this one create pore water pressure. Now, if the pore water pressure at any point is equal to the total weight of the soil there, then basically your effective stress would be zero at that time. Okay, if your effective stress is zero, let's say for any cohesionless soil, then basically your tau would be zero, shear strength would be zero. So what is shear strength zero means? This means like this one will behave like a liquid. So that we call the liquefaction, okay? Liquefaction is one of the greatest problems that can happen during the earthquake situation. So let's say here that the four terms, we have to remember that one, that all phenomena that causes a reduction of the shearing resistance and develop large strains as a result of increase in pore water pressure under cyclic or static loading. Okay, that's basically liquefaction. What is initial liquefaction? Is the condition when effective stress is momentarily zero during the cycle. The first time when this one occurs, like your pore water pressure is just equal to the weight of the total stress or of the pressure from the self, like loading, then basically, like the first time when it achieves a pore water pressure that the effective stress is zero, then basically we call that one initial liquefaction. Flow liquefaction. Flow liquefaction is like when in situ shear strength are greater than the steady state undrained shear strength. Okay. The in situ shear stress is basically higher than the strength. Then basically this one will start flowing. That's flow liquefaction. Cyclic liquefaction, when the cyclic loading causes shear strain reversal and initial liquefaction develops temporarily. That's the condition which we call the cyclic liquefaction. So basically the liquefaction occurs due to earthquake is basically cyclic liquefaction. Okay. Now I just gave that, like that boundary that you can see where liquefaction occurs. Liquefaction doesn't occur in clay soil. It usually happens for cohesionless soil. Okay. So when the soil doesn't, like when the sand doesn't have like any shear strength, it starts behaving like liquid, right? This is sometimes we call that one quicksand. Okay, so you can be drowned in quicksand. Okay, anything you just put in the sand maybe sink. Okay, maybe sank. But you can see here that this is a very good, uh, initial understanding that how whether the soil you pick for your construction, is we if this is within that boundary here, this is and this is the boundary here, are most liquefiable soil. Okay, this is the boundary of the soil. This one has potential uh, for liquefaction. Okay, so if you have soil, you can see this is basically sand here. Okay, but we usually don't use pure sand for any embankment. It's not a good idea at all. Okay. Anyway, so I ask you one of the questions like, how do you know that whether your soil is within the boundary of the most liquefiable soil or within the boundary of the potentially liquefiable soil or outside of the boundary? Okay, so I gave you 5 or 6 soils and I ask you like, hey, just try to say which one has the, you know, so what you can do here that you can just get like some points, like let's say 3-4 points for this line here. Okay, you can just see like, hey, this is, if you talk about this point here, so this is actually 0.2. There's the grain size diameter and the passing is, let's say, 95%. Okay. Similarly, you can just draw that line here and just try to see this point here. Or you can just draw that line for 50%, what is the grain size, and for 20%, what is the grain size. So if you find out like from that case, like, hey, what is your, let's say, D90, D60, D40, and D20, okay? And then read that one and then plug these values in the soil that I gave you, and then draw that 2 lines there. So anything in between this boundary is actually most liquefiable soil. And then you just try to draw these 2 lines here and say like, hey, this is the potential liquefiable soil. And if you have any soil outside that boundary, then you can tell that like, hey, this soil is not gonna go. Now, sometimes you can see like the some part of that soil is within that boundary, but other part is not. Then basically this one will become like partially, like liquefiable. Okay. Here is the other data we see that somebody, tried to do that one using the tailing slime, means like the refuge um, from the tailings. So you can see, even though this is like boundary for most liquefiable soil here, but the range of grain size of tailing slimes with low resistance to liquefaction, that one goes like this here. So this is for normal soil, okay? But this one is for tailings slime, okay? So you have to consider if you want to fill your, embankment with tailing slimes, okay? So that's basically it. If you have any question, uh, please don't hesitate to join me in our Zoom session. And thank you for your attention.